I will. It's great that I talk after immediately after Ellen, but I will talk about something about entanglement as well. And I can remove I will focus on the entanglement of the electrons as indistinguishable from many-body states. So there is I plan to merge a machine learning topic inside, but I found it's very hard to squeeze everything into a 30 minutes talk. So you will see how I merge it in the end. Yeah, click on it. Oh, yeah. Okay, great. So to give a brief introduction about why and how we measure entanglement is if we think about the classical bits, the classical computer, how we realize the two algebra in the classical bits is we use the 0 and 1 states, and in a quantum in a qubits we have a superposition of the entire SU2 space to represent all the superpositions. So if we, for example, want to represent a double position complex number, we need 128 classical bits, and we need only 1 qubit. So this is of course, the idea. But when we realize everything in hardware, it doesn't seem to be very straightforward, because for the classical bits, you can realize it by the p-n junction. And p-n junction is controlled by the voltage, the gating voltage, and how the connectivity between the two electrodes. So we can realize the control of the 0 and 1 gates by electrons in the classical bits. And when we realize the qubits, what do we use? There are multiple ways to do that, but there are most popular ways are still using electrons. We use quantum dots, use superconductor, and more recently use the trapped ions. So there are all electrons, and why do we call some electrons to be classical, some electrons to be quantum? The truth is, it doesn't matter what you talk about. What matters is the entanglement. So when you put the electrons together, when you in a classical computer, you can scale up, you can make a lot of transistors, billions, 100 billions of transistors together, can make the very efficient HPC computers like the NVIDIA H100 or Apple A17. These are the transistors with billions and the chips with billions of transistors. But their computing power scale linearly with the number of units in the end. So the idea for a ideal quantum system, quantum computer is you want to have the qubits entangled with everything, and the computing power should scale exponentially with the number of qubits. But this is in the condition that we have the entanglement between all qubits. You have the all-to-all entanglement. In reality, if we want to make a device, what we usually encounter is we only have the entanglement controlled by some gates, local gates between the qubits. So that's the typical picture of the quantum computer. It's an IBM quantum computer. You only have qubits controlled by the nearest neighbor gates. So in reality, the computing power still only superlinearly with the number of the qubits. That's also because of entanglement. The entanglement between qubits are not the all-to-all entanglement. You only have some local entanglement control. So that's the entanglement and not the electron, which matters in the many-body system. So the entanglement in terms of the quantum information, what we learn in the textbook is defined as how the system is separable from another subsystem. If we have a subsystem A and B, we have a cross product between the wave function of A and wave function of B. This is called a separable state, a non-entangled state. But if we cannot find the direct product state, we call this is entangled state. And the typical way to represent entanglement is using the spin states, as Alan just discussed. we can we can use the example of the product of upspin and downspin for the separable state, and a singlet triplet state to represent the entangled state. But there is a additional concept in terms of entanglement, which we usually call entanglement depth. So that determines how large your Hilbert space is and related to the complexity of qubits. So if we use this shaded regime to indicate the fluctuation of the singlet triplet, you can have a alignment of all the classical spins. This is a separable state when you have many spins. And if you have some of the spins being entangled, but only entangled in pairs, like the singlet and triplet pairs, this is the entangled state. Or you can have more spins in the same block, irreducible block, they entangled in 3 spins. This is also called entanglement. But to distinguish these two different things, they are different. They have different Hilbert space dimension because you can see that you have different number of qubits to control. The number of coefficients to control. To distinguish them, we call this type of state the bipartite entangled state because you only have at most 2 spins in the same product. And in this case, we call it tripartite state. In terms of classification, this is a similar figure Alan just showed. We can classify all the spins in the following figure. You have a separable state, and the bipartite state is on top of it, tripartite and four-partite. So this, the collection of separable and bipartite state is, we call it 2 producible state. That means you have no more than 2 parts of spin being entangled. And the collection of separable, bipartite, and tripartite, we call it the 3 producible states. So this number of producible state, K producible state, we call this K the entanglement depth. Just to make sure we are on the same page to discuss the concept. We are not really discussing whether the entanglement exists. It's more about classifying the entanglement depth in a many-body system. So this is a concept that I borrowed from the quantum optics community, cold atom community. This has been studied for decades. In ultra-cold atoms, there are sufficient ways to measure the entanglement and entanglement depth. The major idea is you can use entropy. You can use the purity of the state after you trace out the subsystem. If you have a product state, the density matrix is also product. And if you trace part of the system, this is still a pure state. But if you have the entangled state after you trace out part of the system, it becomes mixed. So this mixture, this purity of the state, can be precisely determined in ultra-cold atom measurements by preparing the identical twin states, many-body states. You can do the so-called interferometry of the many-body interferometry of these 2 identical states. So this is a work done by Marcus Werner group a decade ago. You can prepare a pair of twin states and use the collapse of the 2 states to measure whether you have the mixed state or the pure states. The basic idea is because of the fermionic statistics, the mixed state will always give you an odd number, and the pure state will always give you an even number. So if you see an odd number odd number of particles appear in part of the system, that's an indication of the mixed state. So you can.
Sir, I'm confused. This is coming from Homo-Mandel interference, so this is purely bosonic statistics here.
Oh, this is sorry. This is a bosonic experiment now. So I want to use this as an idea of indicating how they use the mixed state to measure the entanglement. So yeah, this is a idea from the cold atom community where we have the preparation, we have access to the identical twin states. You can make the many-body interferometry. But in solid state, we do not have such a luxury tool. We cannot prepare 2 materials to be identical to each other, precisely identical to each other. And we also do not have access to the size resolved wave function. So there has to be some compromise we make. as I just discussed, we have to measure it. We do not have to precisely measure something, but at least we should be able to measure to indicate something. So this idea has been widely existed in the field of correlated materials. We usually call it correlation effect. Is if you look at a non-entangled, a non-interacting system, the ground state wave function is written as a Setter determinant from C. Then we know that according to Wick's theorem, all the multi-particle response function can be decomposed into products of the single particle wave function. So if you measure alpha spectrum and you measure a neutron scattering, X-ray scattering, they should be fully represented by each other. So you should be able to reconstruct the entire many-body with many multi-particle wave function from the single particle wave function. But if you have the correlated system, you have the entanglement of the wave function, the Wick theorem doesn't work, then you cannot reconstruct a scattering spectrum from a single particle state spectrum. This has been known for a while in community as an indicator of the correlation effect. So the idea I want to discuss is whether we can use this difference to classify entanglement and not just to show there is a correlation, but to show how strong you have entanglement in the system. So this is a point I want to mention a little bit about the machine learning because we recently had a work by a domain adversary machine learning neural network try to combine the experimental data, experimental spectral data, and theoretical spectral data. So you can overcome the limited data volume in experiment. You can use a lot of simulated data and only a small amount of simulated experimental data, using the domain adversary method to combine the domain and try to bridge the gap between the two subsystems. Then you can classify fluctuating superconductivity from a long-range order superconducting state. Yeah, I only want to mention very briefly because this will be very different from the fundamental topic I will discuss. Okay, what I want to discuss in the next few minutes is how we can use the difference between two spectrum to classify the multi-party entanglement in the many-body system. Okay, so the idea we want to use is the so-called entanglement weakness, as I just introduced. Entanglement weakness is not a precise measure of entanglement. This is more like an indication of it's like a lower bound of entanglement we can indicate. So the idea is if we can define an operator that can be measured in a many-body state, and this operator will be bounded by some value in the many-body state. You can have a minimal value and maximal value of this state for a class of wave functions. This class of wave function is the key producible states. So if we traverse all possible key producible states and find there is a maximum value for the observable and the minimal value for the observable, then we can use this maximum and minimal value to indicate, okay, this is the valid region of the observable. And if this maximal or minimal, the upper or lower bound satisfy the condition that they are monotonic with k, means when k increase, the upper limit also increase or lower limit decrease, then we can call this observable a entanglement weakness because by measuring it, we can tell ourselves what's the region of k entanglement depth we end up with. So that's the idea of entanglement weakness. Again, this is not a precise measure because you only have inequality. You do not have a precise value of the k. You only have the lower bound of k, and it's not unique because you can identify. You can design different operators. Alan just discussed the tangle, one tangle, two tangle, and entanglement. There's quantum spin, quantum Fisher information. So if you have a bad entanglement weakness like this, the control penetrates all different regions of entanglement, then they won't do anything. You will get the equation giving you no information. But if you have a good design of entanglement weakness, you should almost be parallel with the boundary between the the different entanglement depths. I want to give a small example, more like a textbook example before we go to the results. So if we talk about the spin state, the classical spin state, we can try to distinguish from a spin singular triplet state by measuring the total spin. Of course, if you just measure the total spin itself, you find that they have the value of the total spin end up with the same minimal lower and upper bounds. But if you subtract off the classical component, if you measure the fluctuation of the total spin, you will find the classical total spin go to zero, fluctuation go to zero. So apparently it's classical. And for a spin singular triplet state, the total spin square, the deviation is bounded by 4s squared. And you can you can use this trick to distinguish the classical and the quantum state and the entangled state. And this upper bound actually means something because you won't be able to always find the correct direction of the classical spin. You may find this z-oriented when you measure in x direction. So you end up getting some uncertainty by measuring a classical state. Upper bound can be 2s squared if you measure in the x direction, and the upper bound for the spin singular state is the same, it's still 4s squared. So if you measure the total spin square, which is end up being something between 2s squared and 4s squared, you know that this has to be an entangled state, not a classical state. That's the idea of the entanglement witness. You can normalize by a number of spin, and you can convince yourself that if you keep increasing the irreducible blocks of the entanglement, you will get higher and higher bounds. So that means the total spin is a good quantity that can indicate the entanglement depth in the spin system. And this brings to the idea of the spin quantum Fisher information, because the total spin is nothing but the structure factor. It's a one moment specific momentum, Q equal to 0 structure factor. So if you generalize into a structure factor at all different momentum and the Fourier transform, you have the quantum Fisher information defined as the SI Sj minus the average of Si and average of Sj. So the fluctuation, the standard deviation of the spin at I and j. So as we just discussed, the upper bound of this quantity is controlled by the entanglement depth k times the s squared. And because there is a factor of 4, there is also a factor of 4. That's because of the convention. So we can use this quantity to measure, to identify the entanglement depth in the spin system. So this is related to quantum information and quantum metrology by the Fermi-Rao bound. This is the bound of the uncertainty when you measure a system by unitary transformations, unitary measurements. The uncertainty, the variance is controlled by the quantum Fisher information. And it's also related to neutron scattering, as Alan just showed, very beautiful data. You can measure the neutron, the overall spectrum and subtract of the classical peak. I think that's related to what Leon just asked. The reason why we need the spectrum is we have to subtract of the classical, the elastic peak, because there you have to remove the classical components. Okay, so this is what I think Alan just showed, the example of 1D spin chain, and we compared with the EMRG results, the QFI quantum Fisher information extracted from the experiment perfectly aligned with the QFI extracted from the wave function of the EMRG. So you measure at the final temperature, you indicate at least a 4-particle entangled state. Of course, at the 0 temperature, in the end, you will get infinite entangled state as a 1D spin chain. But it's at least the indication of multi-particle entanglement at the final temperature. So,
so sorry for the triangular lattice, it's not triangular.
Sorry,
my quantum Fisher information was for the triangular lattice.
Yeah.
Should be triangular rather than.
Yeah, I will mention triangular in a moment. This is the earlier example of the 1D chain.
So we define this tape reproducible pure state.
Right? Yeah, we can. That can also be generalized to mixed state. There's a natural generalization, but the result I will show is on the pure state. Yes.
Yeah, I mean, yeah, related to the Alan's question, answer to my question, like at high temperature, right? We're not necessarily in the pure state.
Yeah.
So you're saying these bounds has a counterpart.
Yeah, this bound can be generalized literally to finite temperature.
Okay, thanks.
So what I want to talk in the second half of the talk is well, is the real part of the work is that we have something slightly different when we move from off from spin system to electronic system. In the spin system, in the many-body spin modes, we have a separable mode, and we have a we will identify the distinguishable modes. We can label the mode 1, mode 2, and our wave function in the many-body spin wave function is written as a direct product of these different chunks of the spin system. So the maximum, the depth of the largest irreducible partition is called our entanglement depth of the entire system. That's the definition of the quantum Fisher information. But for indistinguishable,
What's the definition of mode?
pardon?
Mode? What is mode mean?
Oh, mode, that means you have a local spin. You have like a qubit. You have a qubit at some site. So all these modes can be labeled. But if we have an electron, we have a many-body electron, indistinguishable electron, they cannot be labeled. And you have a many-body wave function, and the fermionic state is just a many-body state, many-body wave function without any labels. So the first thing you have to consider is for a fermionic state, the counterpart of the separable counterpart is no longer the direct product state. We know that the two particle, if you have two electrons, if they do not have an interaction, the two particle state, the two particle wave function is not the product of the wave function 1, 2. It's a stator determinant. You have to satisfy the anti-symmetry exchange. So that means you cannot just generalize the QFI in the same way, because you just the electron have this natural super exchange. So if you just generalize it using the idea of the direct product, you will find even for Fermi C, everything is entangled, and that's not the way we identify entanglement. So for electron, this has been generalized by Philip Hogg 3 years ago. So they instead of using the tensor product of the wave function, they generalized it into a creation operator. So the creation operator is irreducible superposition of many electrons inside a partition. Then the product, as long as the wave function can be written as a product of all these creation operator, then we can count the number of orbitals inside each creation operator and find the maximum. That's the generalization of entanglement depth, which overcomes the anti-symmetry problem. But there are also other issues we have to consider, because for electron, there's no natural orbital. And for electron, the orbital are just artificial ideas we plug into the material. In reality, it's different from the qubits and spin system. You have the natural local spin there, they are visible. But for electron, the orbital just the basis we expand the wave function. So you for Fermi C in the momentum space, you will find is non-entangled in this framework. But if you do a Fourier transform into real space, it becomes entangled, and that doesn't make any sense. So we have to define something which is transitional invariant under basis rotation. So if you do the single particle basis transformation, you have to find all these possibilities and find the entanglement depth, the minimal entanglement depth in all these bases. There is a best basis, and in this best basis, the system is the minimal entangled. So we generalize this idea by including a Gaussian transformation on top of the creation operators, and the entanglement depth is then generalized into a minimization over all possible Gaussian transformation. Well, Gaussian transformation means a basis rotation of a single particle. So after this generalization is not finished, because for electron there is another issue. In reality, in real materials, we do not have a well-defined filling. We even for hydrogen atom, they have infinite orbitals. We just truncate our bases in some sense. So the electron usually have a fractional filling. So instead of counting how many number of orbital, there are always some idle orbital in the end. we should change the counting of orbital into the count of the number of particles in the system, and particle or hole, whichever is the smallest. Right? So that gives this is an example. We count the maximum number of maximum irreducible part with the electron number, and we count the minimax problem. And for this example, they give us the entanglement depth being 2. So using this idea, we can try to identify the entanglement depth of the electron with irreducible particles. So the question is, what's the good quantity? What's the good entanglement weakness that can identify entanglement depth for electron? So this entanglement weakness has to satisfy the following criteria. First, it has to be resilient to the antisymmetry we just discussed. So that's the requirement for entanglement depth. It has to be invariant under basis transformation. It has to be monotonic with the entanglement depth. That's also the definition of entanglement weakness. You have to have a monotonic relation, otherwise you cannot find their entanglement depth. And it has to be measurable. Otherwise, we just talk about some artificial thing. So in the end, we found that this can be done by something called the two-particle reduced density matrix. That's a different reduced density matrix as we usually talk about in quantum information. This is a kind of chemistry concept of the two-particle reduced density matrix, which is a 4-point fermionic correlation, the Ci, Cj, Ck dagger, Cl dagger. So for the 2-RDM, that's a quantity that has been studied widely in chemistry, like primarily by David Mazzotti and other colleagues in the past 3 decades. So if you think about this quantity and merge some indices, if you merge the I with K and the J with L, you get the spin-spin correlation or charge-up. So the quantum feature information is actually a subset of the RDM. But what's more important is if you want to subtract off the classical part. The RDM is something, but it's not very efficient as we just talked about the total spin. You can subtract off a single particle, the RDM, the 1 RDM part, which is the two fermion correlation, any combination of 2 fermion correlation, because if you have a Slater determinant, you have a weak theorem, and that will vanish, the subtraction will vanish in the end. So once you subtract off the classical counterpart, you get the so-called cumulant RDM or 2C RDM. This quantity can be very sensitive to entanglement because it vanishes in the classical limit. So using this quantity, what we want to show is we will satisfy all the criteria. It vanishes at the Slater determinant, the Fermi C, so it's resilient to the antisymmetry itself. We won't misclassify a Fermi C into entangled state. And this quantity is not basis invariant, but it's unitary under unitary transformation. So the tensor, this tensor, 2-RDM tensor, transform with U dagger when you have unitary basis transformation. So once you see something like this, you know immediately what's the invariance, which is the eigenvalue, the singular value of the tensor. So the singular value becomes the invariant property of the basis transformation. So while we to make things more easier to calculate, we can flatten the tensor into a matrix by grouping some pairs. Well, this is not a precise estimation of the singular value, but we actually compare with the tensor decomposition that extreme eigenvalues are consistent most of the case. So using this idea, we can demonstrate that this tensor, this 2-RDM, is separable when we have the structure of the partitions. So this 4-point tensor can only to be calculated within the irreducible partition. So this becomes the superposition of all the direct sum of all the irreducible partitions. So the eigenvalue, the maximum eigenvalue, becomes the maximum eigenvalue of each irreducible block. So we reduce the many-bodies problem into each irreducible block. That's like a irreducible the counterpart of the system. So we only have to analyze the extreme eigenvalues within some standard building blocks of the system instead of all many-particle systems. So at least we only have to find the supreme, the tight upper bound for the eigenvalue of 2 RDM for any improducible state. Then this can classify the entire many-body system without worrying of how many particles we have. So this upper bound has a nice result of this. For 2 producible states, it's something that has been proven by the quantum information community, Ignacio Sirac and a few colleagues. How many time I have?
Well, we got 5 more minutes.
Okay, 5 minutes.
Into questions. Yeah.
So if for 2 producible states, we can have a full representation by the so-called standard decomposition. Then you can have exhausting sampling of the system, and you can prove that the maximum eigenvalue is actually 3/4, and minimal is 1/, is a negative 1/4. So that means the supreme for 2 producible state is 3/4. And we can, this is a numerical example, numerical sampling of the state. You can see that it's exactly the 3/4. We can move to a 3 part. I will speed up a little bit. We can move to a 3 producible states. There's no exhausting representation for 3 producible states, but if you believe that GHZ state is the representation of the most entangled, maximal entangled state, then the GHZ state can be calculated. The maximum value is 5/4. And we also calculate the W state and its generalization, which is the spin state. And that also gives the same value. So for the
2 reproducible states, you don't mean the system has only 2 electrons.
Well, the block has only 2 electrons.
Okay.
So the system can be infinite electrons.
Downstream.
So well, we can generalize to any k producible state in the same way. Mathematically, we can prove that it's the upper bound increased with k as a half of k minus a half. For k larger than 2, for k equal to 0, k equal to 1, it's actually 0. So this is we found this is a numerical experiment. We just skip it. So in the end, we demonstrate the 3 criteria. It's resilient to the antisymmetry. It's unitary invariant, and it's monotonic with incumbent depth. The only thing we have to prove is measurable by solid state spectrum. The idea we use is nonlinear spectroscopy. I usually talk to X-ray experiments, so I use the example of RIX, resonant inelastic X-ray scattering, as a way to measure it. So in the resonant in the RIX spectrum is represented by the so-called Kramers-Hessenberg formula. You have an intermediate state with a core hole, and this core hole is usually believed to be immobile during the X-ray process, usually happening in the 10 femtoseconds. For the X-ray emission and X-ray absorption and emission process, the core level is usually believed to be immobile at the same atom. But this is not usually the case. I mean, we did some initial calculation. We found that the core level has a bandwidth, so the core level can move during the X-ray process. So if you, I will skip this. If you have the core level moving, then you actually measure the C dagger C, the creation and negation operator at different sides. Then your RIX spectrum, when you consider the core moving, is written as a superposition of all this probability expansion of the core level kinetic energy. And this becomes a, we'll move fast. This becomes a momentum dependence of the incident and scattering photon. So you can use the momentum pattern of incident and scattering photon to classify these different C dagger C pairs in the when you consider core level motion. This is an ED simulation for RIX. You can see that when we consider core level motion, the different incident momentum will give you different spectrum with although the same momentum shift. And we can use this to classify to quantify the multi-point correlation function. That's the exact result. The dark blue, the exact result, and light blue being the RIX measured one. They align pretty well. This is a numerical result, so there is always a finite energy window. You have numerical error. I want to mention a little bit that we have to subtract of the classical part, which can be measured by APAS, single particle part. Then subtract of the RIX from APAS, you can get most elements of RDM, not all elements of RDM, because you only consider the nearest neighbor motion of the core level. You do not do perturbation for long range. So this is a picture of all the distribution of RDM in the precise wave function. That's a Hubbard model simulation. I flattened the indices into pairs, so it's a matrix. You can see the positive and negative values of RDM. The size of the points indicates the size, the value, the absolute value. So it turns out that all values that can be measured by RIGS can almost cover all the important elements in RDM. So the RIGS cannot measure all elements of 2RDM, but it measures most important elements. So the eigenvalues measured by RIGS can be a good representation for the RDM, the eigenvalue calculated by 2C RDM. So the last point can be checked. So I want to quickly show the example, and then we can finish. For the 1D extended Hubbard model, we did the DMRE simulation, and we found, okay, the RIGS can estimate the RDM. Well, there is some numerical error because of we miss some elements, and RIGS has we integrate in a finite window. So according to our classification, the boundary is 3/4 between the two producible and three producible state. So in a doped 1D chain, 1D extended Hubbard model is two producible state, and this is consistent with this is a quantity better than the spin QFI, because if you use the spin QFI to measure to identify the entanglement, you will find you cannot exceed the first boundary, because this is when you dope the system is no longer dominated by spin excitation. So spin excitation is so weak, and spin QFI won't be able to be efficiently characterize the entanglement. Similarly, if you do the triangular lattice Hubbard model, you can characterize the entanglement with the spin liquid phase. You can have the maximum entanglement in the spin liquid phase, and that can be perfectly characterized by RIGS measurement. So this state is a four particle entangled in our cylinder calculation.
When you say it's m particle entangled, you mean at least it's m.
At least, yeah.
Because the actual ground state probably contains 5 times value of 6 particle entanglement.
Exactly, yeah. Because in DMRT you actually have bound dimension, so you actually have you may have a more entangled state. In reality, it's just if we design an experiment, the experiment can only calculate and identify at least this. Okay, so this is consistent with the QFI identification when you have the spin dominant phase. But when you are in the metallic phase, the electron entanglement can still work. You can still identify this is a coordinated state, not a Fermi C. But at some point, the QFI will not work because this system is too weakly spin dominant. It's no longer spin dominant. So the take-home message is whenever the system is a spin dominant, the message for the result from the electron entanglement and the spin entanglement, they give the same result. So it covers all the QFI information. But when the system is no longer spin dominant, you can still use the electron entanglement to identify electron witness to identify entanglement. Okay, and this is very different from the entropy, the entanglement entropy. Because if you're familiar with the MRT, when the system becomes gapless, the entanglement entropy is going high. But this is not the case when you consider the system, the complexity of the system. It's just a static determinant. Okay, so I want to stop here and to briefly summarize. We discussed two things. We built the framework for the entanglement depth, or which criteria has to satisfy for indistinguishable particles to distinguish with a spinning system. And we also discussed that this can be realized by 2C RDM and RIGS measurements. Okay, I'm ready to take questions here.
It's one question, or else we're cutting into dinner. So this idea of using the NRDM and computing its entanglement, Schutten's introduced this 15 years ago or so. It's the particle entanglement, right? You can just compute the entanglement of the RDM. And so what you wrote as entanglement entropy on that last slide is just the spatial entanglement. So if you did the entanglement of the RDM, you would get the exact opposite. So anyways, there's a lot of literature on this one. And particle entanglement. We worked on it and many others.
There's
many provable things. And anyways,
I know. So there premier work by David Mazzotti and some co-workers in the in the field. And yeah, the main idea is to show what's the criteria we need for the witness and why this can be measured by spectroscopy.
Thank you. Thank you. Microphone. Oh, that's good. Let me say very quickly. So,
We're speaking tomorrow on Zoom.
let me do it. Yeah.